Um, yeah, administratively, not so much going on. Of course, we'll have a quiz this week because we got the exams back, and because of fall break and whatnot, we didn't have one last week. But so the quiz this week will cover 15.1, 15.2, 15.3, and then today's material 15.10. So those are the topics that you should be preparing for the upcoming quiz this Thursday. Otherwise, I don't think I have anything else administratively. Any questions before we jump into our math? All right. So then, today we're talking about 1510. A little bit out of order, but this is kind of the algebraic stuff that you want to be able to switch your variables out. And so with moving up this 1510 section to where we have it in our schedule, we'll be able to explain why when you transform into polar coordinates, so all of this, right, we've done double integrals now in Cartesian, kind of to their full extent, first over rectangles, then over general regions. And the next thing that we'd like to be able to do is to do double integrals in polar coordinates. We'll then move into triple integrals, and we'll do triple integrals in Cartesian, and then we'll like to change coordinate systems and do cylindrical and spherical. So 1510 here will give us all of the really the algebra behind why you need this certain term when you switch variables. And so that's the main topic and why we have this here today. So first I want to talk about transformation equations in general, right? Of course, the ones that you should have in the back of your mind are the ones that transform you into polar, right? Because those are the ones that we'll be using in the immediate future. But if you have just any old transformation equation, we'll use parameters u and v in our first example here, right? The first thing that you can do is how can you transform points, right? So how can you go from a uv point to an xy point, or vice versa? How can you go from an xy point to a uv point? One of these is very simple. You just plug in, right, into your equation and you get out the answer. The other one, you have to solve a system of equations, right? And it's not the worst thing, but it's also not as easy as the other way, right? And so this gives you kind of these transformations between different coordinate systems, either the xy coordinate system or, in this case, a uv coordinate system. In order to do the calculus that we're interested in, you do need to be able to take derivatives of these things. And so we need continuous first order partial derivatives for a lot of the calculus that we'll be doing to make sense. So that's what that was all about. And then we do want these things to typically be one-to-one. And that's so you kind of maintain some semblance of areas and whatnot, and you can create this inverse transformation here that goes from the xy plane into the uv plane. All right, of course, the main meat of this, right, is with the example. And so we did an example for a while of how do you transform regions. And so we started off with something, right, in the UV plane, and we transformed this into something in the XY plane. We did have to do this kind of very much like when we did absolute mins and maxes, right? We have to consider each boundary individually. And so we look at each boundary, we can go ahead and make the transformation and see what this then looks like in our other coordinate system. So today we're going to be getting into the calculus behind, okay, now that we have all of this algebra built up, what do we actually get out of this calculus-wise? So that's the pre-class video in a nutshell. Any questions before we jump into the new stuff for today? All right, then. So let me switch over here. And the first thing that I'd like to do is just try to naively do some integral here and see what happens and see if everything works out or if we need to make some modifications. So in my example, we have a very nice function, right? No matter what x and y are, the function always outputs 2. We also have a pretty nice region. So it's just a unit square. That is, x's range from 0 to 1. So again, these are the x values. And the y's range from 0 to 1. Those are the y values. And so if I was to just straight up evaluate this integral here, Well, this is going to be an integral. Again, we're doing y first and then x, but both of these bounds are 0 to 1, 0 to 1. And the function is just a nice even 2. So we can go ahead and evaluate this as it sits. You can notice that this function here is so simple that you can write it as a function of just x's times a function of just y's. And because we have these constant bounds, you are allowed to go ahead and split this up. So this could be the integral from 0 to 1 of 1 dx times the integral from 0 to 1 of 1 dy. And this was a property that we got, I believe, in our 15.2 notes, right? And so when we integrate these things, well, the integral of 1 dx is going to be x. Evaluate that from 0 to 1. And the integral of 1 dy is going to be y. Evaluate that from 0 to 1. And you're going to have 2 times 1 times 1, which is just a nice even 2. So now we're going to apply some transformation and see what happens. So we're going to find a region S in the UV plane that corresponds to R in the XY plane. And then our goal is to evaluate out and see this integral where we're going to have U's and V's. And ideally, this transformation that we apply would not alter our answer. We would like a new technique to be able to solve double integrals without changing the answer. So my goal or my dream is at the end of this, we should still get out 2. If we got something else, then it's a bit concerning, right? And then we can't use this technique to calculate out some difficult integral for x's and y's. All right, so for our transformation, it's a pretty nice one. We have our x coordinate is just 1/2 of u, and our y coordinate is just 1/2 of v. So if I wanted to figure out what does my region look like in the UV plane, that corresponds to x's ranging between 0 and 1 and y's ranging between 0 and 1, right? So I could sketch this even. So in the xy plane, we know our region looks like a 1x1 unit square here. And this really has 4 pieces to it, right? So we have, oh, that's a really bad 1 there. Sorry. 1 there, much better. All right, so this really has 4 pieces. X equals 0, x equals 1, y equals 0, y equals 1, right? Those are all the boundaries here. But nicely, when I go and I plug these things in, right? So if I plugged in x equals 0 into my transformation equation, this would be 1/2 u is equal to 0. We can find that this corresponds to just u equals 0. And likewise, if I was to plug in x equals 1, the upper bound, right, the right-hand side of my square here, well, 1/2 u equals 1, again, my x value is 1 here, just gives me a u value of 2. And likewise, if I was to do this same sort of deal with my y's, right, so y equals 0 and y equals 1, I hope that you can maybe quickly see that this is going to correspond to v equals 0 and v equals 2. It's the exact same algebra moves. So in the UV plane, u's range from 0 to 2 and v's range from 0 to 2. And so we just have a bigger square. So rather than a 1x1 square that we had in the xy plane, we have a 2x2 square in the UV plane. So this would be our region S, this would be our region R. So the region S in the UV plane. Okay, so if I wanted to set up my integral then, well, my u's should range from 0 to 2, and my v's should range from 0 to 2, dv, du. My function, right, where everywhere I see an x, I would need to plug in my 1/2 u, and everywhere I see a y, I need to plug in 1/2 v. Well, my function is so simple that actually you don't really see that come up at all, right? If there had been any x's in my function, I would have needed to swap in 1/2 u. And if there had been any y's, I would need to swap in the 1/2 v. to get this in terms of u's and v's rather than x's and y's, but that didn't really come up at all. So now when I calculate out this integral here, we're going to get, right, and again, you can split this up. We can do 2 times the integral from 0 to 2 of 1 dv, and the integral from 0 to 2 of 1 du. And so when I integrate these things, oops, it's a bad u, I get 2 times 2 times 2, which ends up being 8. And so it seems like this transformation has affected my answer. The answers from A and C are not the same. And so as it sits right now, I can't use transformations to help me evaluate out integrals. But I'd really like to. And so we need to actually remember something from our algebra class a long time ago. And not every algebra class necessarily visits this, but some of them do. And that is that determinants, so determinants of matrices, help measure change in area for a transformation. 3 Blue, 1 Brown make a lot of really nice videos with graphics and whatnot. If you haven't seen them, they spend a lot of time in great detail explaining concepts, and they do a really nice job. And so we could spend an entire 50 minutes talking about this concept in our class. Unfortunately, we have to get to the calculus. And so I invite you, if you'd like to, if you haven't seen this before, right, do watch their video, and they can explain why determinants help measure this change in areas. So we're going to bring up a determinant to help us split this gap. Why did this 2 turn into an 8, and how can we fix that is going to be answered by a determinant. The determinant in question, or the determinant that we need, is the Jacobian. And hence the name of this subsection, Carl Gustav Jakob Jacobi's magical matrix here. So this is Jacobi from Jacobian. All right, so the notation goes like this. It's a partial of x's and y's divided by a partial of u's and v's. So that is notation. That means basically you're taking all combinations of your xy functions and taking partial derivatives of them with respect to u and v and inputting those into a matrix. So we're going to have the partial derivative of x with respect to u, and then the partial derivative of x with respect to v. So basically you're holding your first variable constant, and then you're working along your variables u and v here in the first row. And then in our second row, we'll have all of our y information. Again, first taking a partial derivative with respect to u, and then taking a partial derivative with respect to v. Of course, we know how to calculate out 2x2 determinants. Oops. So partial of x with respect to u times the partial of y with respect to v minus the partial derivative of x with respect to v times the partial derivative of y with respect to u. So again, just this cross multiplication, subtract the other diagonal there. And so let me show you kind of what this determinant is doing here. So we've had a kind of a similar picture here. Oops, and this should be a V. In the UV plane, maybe we have some interesting region, which I'll call R. And we can go ahead and break this up into lots of little subregions here. And maybe each one of them has a width of delta U and a height of delta V. So here would be a little area, right? If we multiply delta U times delta V, we'd get a little area here. And then we have some transformation equation, which takes this into the XY plane. And maybe each one of these lines looks, slightly different. So maybe we'll do something like this in our XY plane. And if we took this rectangle and we mapped it into our XY plane with some transformation, this, of course, has some delta X and delta Y associated to it. So maybe delta X and delta Y associated to this. And my claim is that this delta X times delta Y, which we've used before, this is maybe just the change in our area here, that this is approximately equal to the absolute value of our Jacobian times delta U, delta V. We know when we apply calculus to these things, as they get smaller and smaller and smaller, right, these delta X and delta Y's have a habit of turning into dx and dy. So likewise, right, this is saying that if you want to transform your areas here, this delta X and delta Y business, into something with du's and dv's, and you want to maintain equals, right, you really need to include in this Jacobian here. Before we get to that, we'll kind of put this into a nice big box right here. But before we get to that, let's just get a little bit of practice really quick in calculating out a Jacobian. So here would be a perfectly fine, maybe a multiple choice style question or something for a quiz or an exam, or certainly within web work as well. So we have an X coordinate and a Y coordinate for our transformation. And so the Jacobian, that is all of these partial derivatives, is equal to, so first you take the partial derivative of X with respect to U. So I'm kind of very focused on my X equation for a little while. If I take the partial derivative of this with respect to U, I'm going to get 2U. On the other hand, if I take the partial derivative of X with respect to V, I'm going to get negative 2V. So in my first row, I have all of the X stuff, right? The X partial derivative with respect to U, then with respect to V. In my second row, I'm going to have all of the Y stuff, right? A Y partial derivative with respect to U first, then with respect to V. Then I'm going to take the determinant of this. So 2U times U is going to be 2U squared. And then I'm going to minus a negative 2V squared. Right? 2V times another V gives us the 2V squared. So this right here is our Jacobian calculation. All right, and then finally, the big theorem that ties this all together. My claim is that the Jacobian is exactly what we needed in order to maintain equals through transformations. So that is, if you start off with a function with x's and y's, and again, you could integrate this with respect to y first or x first or what have you. And this is over some region R in the xy plane. That this is then equals to the transformation. So R is going to go to S. We're going to have U's and V's here. So everywhere we see an X, we're going to plug in our X transformation. Everywhere we see a y, we're going to plug in our y transformation. So that way we have all u's and v's there. We're going to have our dv and du. And then the piece that we were missing before is exactly this Jacobian. And we need to make sure it's positive. So it's actually going to be the absolute value of our Jacobian. And as a side note here, this will also work in triple integrals once we get there, in which case we're going to have x's, y's, and z's. And then we're going to have u's, v's, and w's, for instance. And again, the primary transformations that we'll be using this on are cylindrical and spherical when we transform into cylindrical coordinates or spherical coordinates. So in reality, these u's, v's, and w's are going to be things like, r's and thetas and phi's and stuff like that. All right. So I've been talking for a little while. Let me pause here and see if there are any questions. All right, well, maybe this example will inspire some questions. So why don't we see an example then, and then I'll open it up. Okay, why did I use approximately equals to back here, I assume? So yeah, these are approximately equals to until you take a limit. A limit so the limit that we do for these things in Riemann sums back in 15.1 is a limit as n goes to infinity. This requires you to have infinitely many of these small rectangles here. And so these delta x's and delta y's are approaching zero. They're very, very small. And so when you have the deltas, really, they're not equals to, but as soon as you take this limit as n goes to infinity, then there is equality, true equality. And so in this case here, right, we are swapping out our dy dx for equals to this stuff here, right? The Jacobian, or the absolute value of the Jacobian with dv du. So this is fine, this is equals, but until you take that limit, it's only approximately equal to. Yeah, good question. All right, so I would like to do this example here. We have the integral of 1 dA by integrating r, where r is the circle of radius 1 centered at the origin. We're going to try this first using normal Cartesian coordinates, and then we're going to succeed by using a natural transformation. So this kind of alludes to maybe part A is going to be quite difficult here. So a circle of radius 1 centered at the origin, right? This is the classic unit circle. We know based on the phrasing here that this would have the equation x squared plus y squared equals 1. And so if I wanted to integrate this and use Cartesian coordinates, which by the way, we already know what the answer is going to be, right? When you take the double integral of 1 dA, we saw that last time there was a nice theorem that we had. Oops. I think this was from 15.3. It may have shown up in 15.2, but that the double integral over some region, I think we use d here, of 1 dA is equal to the area of that region. So when your function is the very nice 1, and it's not some complicated f of xy sort of business, but if you just have 1, then this is going to be area. So we know that this is going to be pi r squared. Our radius is 1, so we know that the answer is going to be pi, by the way. So the answer to this is going to be equal to pi at the end of the day. But we're going to try calculating this out in Cartesian coordinates, right? So not using this theorem, but rather with y's and x's and all that sort of stuff, let's actually try to evaluate this out and see how painful it is. So whenever I go to integrate in Cartesian, I need to choose an order of integration. I can either do y's first or x's first. There's not really a compelling reason to do one or the other here. So usually I do dy dx in that case. And then I need to set up my bounds. So thinking about my bounds, if I was traveling in this y direction first, y's go from the bottom to the top of the page, right? Small y values are down at the bottom, large y values up at the top. So we need to talk about how do I enter into my region and how do I exit it? Well, I seem to enter in through the bottom half of this circle. That's how I enter into it. And then I exit through this top half of the circle, right? As if I were to continue moving upward, I would exit my region through the top half of the circle. So I need to explain these using y equals, right? Because again, we have an integral with respect to y first. So I'm going to use my x squared plus y squared equals 1 equation for my circle, but I'm going to solve this for y equals. And when I do that, I have the square root of 1 minus x squared, the positive and the negative, right? Because whenever you take the square root, you need a plus and a minus. So luckily, this negative right here corresponds to the bottom half of the circle. So I enter in through the bottom half of the circle, that is y equals the negative square root of 1 minus x squared. And I'm going to exit through the top half of the circle, that's the positive square root of 1 minus x squared. And then lastly, for my x integral then, remember these are just numbers, and they're the numbers that basically where I was shading, right? So the x values, the smallest and the largest x values. So I have over here the smallest x value, this would be over at -1, because again, it's a circle of radius 1. And the largest x value is over here at +1. So if I was to integrate this and then substitute in, trying to evaluate this out as best as I can. The integral of 1 is y. Plug in my bounds. Minus a negative, that's the plus the other one there. Those are like terms, so if I wanted to take one more line, I could combine these and make this -1 to 1 of 2 root 1 minus x squared dx. But now at this point, I get kind of sad because this isn't quite something I can use a u substitution on. So can anyone tell me if I wanted to solve this integral right here as it stands, what technique would I have to use? Yeah, in the middle here. Trig substitution, yes. So from calculus 2, we could use trigonometric substitution. Yep, you got it 2 online, good. So we could use trigonometric substitution and we could solve for this. But this is kind of a very long problem, right? And so that's what I said, you know, first try using the normal Cartesian coordinates. And that's not to say that if we were really persistent, we could do it. It would just be a bit painful. On the other hand, there's a better way using a transformation. So now I'd like to switch gears and go into B here. So the natural transformation is, well, this is a circle, and circles behave well in polar. So I would like to use a transformation equation into polar coordinates, right? And then use this Jacobian stuff in order to get the final result. So in polar, for instance, I know that x is equal to r cosine theta and y is equal to r sine of theta. So those are my transformation equations. Notice instead of u's and v's here, I have r's and thetas. That's perfectly fine. So when I go and I calculate out my Jacobian here eventually, instead of u's and v's, I'm going to be using the parameters r's and thetas. All right. But let's set up some of this other stuff and then we can calculate this out. So we have a double integral of 1 in Cartesian. I'm going to swap this into our polar stuff with r's and thetas. I'm leaving room for my Jacobian right here. Well, let's first figure out the bounds, right? So in Cartesian, these things were quite complicated. But in polar, I think it's going to be a little bit nicer. So for instance, maybe for theta, if I want to hit all of the points in the circle, can anyone tell me what the theta should range between? Yeah. 0 to 2 pi, right? Because you want to go all the way around the circle. Absolutely. So our theta is going to range from 0 to 2 pi. That's how we can describe this region. Our r's, right? R's, these radiuses, r equals 0 is at the center here. And then r equals, maybe 0.1 would be like this, a little bit farther out. Again, depending on what theta is, it would be specific points, a step of 0.1 away from our radius. And then as you take a little bit bigger step, right, you keep on getting a little bit farther away from our radius. And we want to include all the points, right? We kind of stop. We're outside of our region as soon as we hit a circle of radius 1. And in particular, right, we can go ahead and even solve for that over here. So our radiuses that describe this region are any of the radiuses between 0 and all the way up to 1. Once you go any bigger than 1, you're no longer inside of our circle. So our radiuses are going to range from 0 to 1. All right, and so the last thing that we need is this Jacobian. So maybe going back up here, a partial derivative of x with respect to r. So x with respect to r, we're going to have just cosine of theta. Next up, a partial derivative of x with respect to theta. Well, this is going to be, maybe I need a little bit more room. Negative r sine of theta. Next up, our y stuff. A y partial derivative with respect to r is going to be sine of theta. And a y partial derivative with respect to theta is going to be r cosine theta. Now we can go ahead and take our determinant. We're going to have r cosine squared theta minus a negative, so that's going to be plus r sine squared theta. Of course, if you factor out an r from both of these things, you're going to have cosine squared plus sine squared, which is, we know, equal to 1. So this right here would be times the absolute value of r. So again, you do need, there's kind of two of these vertical bars going on here. There's one that's just in the base level of the Jacobian, right? This means determinant. And then in our formula here, really we need the absolute value of that determinant. So this is the absolute value of r. In this problem, though, it's not going to come up so much because we know r should always be positive. And in particular, they're ranging between 0 and 1. So the absolute value is really not doing a lot here. So now I'd like to evaluate this. I can go ahead and split this up since we have a function of just thetas times a function of just r's, and all of our bounds are constant. We can go ahead and split up our integral like this. Again, this maybe saves one line right now, but when we get into triple integrals, this will be saving on the order of 3 or 4 lines. So if you can pull off this trick, it's kind of, we're just kind of doing this really for practice right now until we get into 3 variable stuff. So when I integrate this, I'm going to have theta ranging from 0 to 2 pi. I'm going to have 1/2 r squared ranging from 0 to 1. And so I have 2 pi times 1/2 1 minus 0. And so my final answer is indeed pi. Notice we didn't even need u sub for this, let alone trigonometric substitution or anything else. So this was a very nice integral once we got it into, again, this natural coordinate system of polar coordinates for our circle. All right, any questions on this problem here? Yeah, in the middle. Yep. Okay.
why it works well, but I'm not like why for the balance for y and the balance for x, which is negative 1.
Yeah, so I mean, this kind of goes into the details from 15.3, right? We tried to really focus on that. And so I can maybe bring up in the video here for 15.3. I think when we were first introducing this is kind of where we got into this. Let's see here. Yeah, this kind of alludes to it here, especially the remark at the bottom, right? So that the fact that the final integral should always just have numbers in it. So no variables. So if you did make it a full equation of x in terms of y's, right, and you had y's in those variables, right, my claim is then when you went to substitute in those y's, that you wouldn't actually get a volume, right? So at the end of the day, when we evaluate out these double integrals are always giving us a volume, and those should be a number, right? So we're expecting that some number like 30, or I guess technically it could be negative because you could have net volume, just like we had in calculus 1 with net area. So you could get an answer of like negative 10 or something like this, and that means that there's more below the xy plane than above it, sort of deal. But yeah, so our setup for these things are always going to be describing the curve as best as possible for your inner limit of integration. So these g of x's here, and then for your outer bound, right, they're always going to be constants. And if you swap the order and you did x first instead of y, then your inner limit here can have y's in it, and that's perfectly fine. But then your final limits of integration will just have, again, numbers in it, so c and d rather than x's. We'll also be explaining this maybe in a bit more detail in 15.7 as well. And in 15.7, we'll get kind of an idea of reducing dimensions. So when you have kind of these both variables, x's and y's, you're kind of in a two-dimensional situation. Once you evaluate out your x integral, you kind of need to smush it down so that there are no more x's left. And you'll see this in your equation, right? There are no more x's at all. And all that you'll have are y's. So you need to really smush your picture down into just the y-axis. We haven't gotten into that quite yet because, I mean, there's a simpler way of just looking at the smallest and the largest values. But with 3 variables, we'll need to reduce from 3 variables down to 2 variables, and then from 2 variables down to 1 variable. So we'll need to reduce dimensions several times. So to some extent, you could imagine that this, after we evaluate out our y integral, this gets smushed down into just the x-axis. So we take our picture and we smush it down so that there are no more y's, and all of the residue is going to live between -1 and 1 here. So that's 2 or 3 different explanations of ways that you could think about this. Did any of those help? Okay, good. And then let me make sure that I'm not missing something in chat here. Okay, good. All right. Well, I'd like to try to do another example here. This one's a bit more complicated. But again, you can kind of see, so this one doesn't have a natural transformation. We're going to use the specified transformation here. But maybe we'll talk a little bit about why this will end up being very useful and actually would save us quite a lot of time. So if I was to, I was handed this integral here, and I'm specified this region. This region is a parallelogram joining these points together. Let me look at what this would look like, maybe in our xy plane. So here's our x's and our y's. And I have the point 1, 2. I have the point 3, 4. 2, 3, 4. That. I have the point 4, 3. And I have the point 6, 5. So 1, 2, 3, 4, 5, 6, 5. So my parallelogram joining these would look something like this. So if we didn't use our stuff about Jacobians and transformations and whatnot, and we were to decide to try to integrate this with respect to y first, right? And I'm traveling up in this y direction. Notice that there's two different ways that we could be entering into our region. We could either enter through this line right here or this line right here. So our bottom limit of integration would actually need to be broken up into these two pieces. What's even worse, maybe, is that then we would also have to break up our top limits of integration, right? The ways that we exit are through either one of these two curves. And sadly, where we enter and exit, right, these actually, they differ. They have different x values here. So sometimes you enter in through the first bottom curve and the first top curve, but then sometimes you enter through the first bottom and the second top. And so you really need to break this down into three integrals. The problem is, too, is that this doesn't get any better, really, if you're going in the x direction first. So if you were to say, well, I'm going to integrate with respect to x first, then you would still end up needing to do this in three pieces. And so this is an example where, I mean, if you really wanted to, you could integrate this with respect to x's and y's, but it would take a long time. Instead, we're going to do this a bit faster, thanks to this information about transformations. So we're going to use this transformation here. It's still going to take a decent amount of time, but it's not going to be nearly as long or painful if we just did in x's and y's. So let me... And let's do this one, as if it were a quiz or an exam question on D2L. And so if I was thinking about trying to maximize partial credit, one thing that I'd want to make sure that I do sooner rather than later, right? We're going to be transforming this into u's and v's, right? So I'm going to do some integral with dv du. We're going to need to, of course, make sure we include in our Jacobian. But even before that, right, we need to swap out our x's and y's for some number of u's and v's. So in our case, right, our x coordinate is equal to 3u minus v over 2. And our y coordinate is equal to u minus v over 2. So if I wanted x minus y, that's one thing that I could do right out of the gate, right, is transform my function, which in this case, x minus y, into some number of u's and v's. The next easiest thing I would say is typically finding the Jacobian. So my second item on the list is probably finding the Jacobian. What's going to go here? And so for this, again, we're going to have, our Jacobian is going to be a determinant of a matrix. We need to take some partial derivatives. First, x with respect to u. So really quick here, I'm going to go ahead and just divide by 2 in both of these, just so we can really see what these look like. So this is going to be 3/2 u minus 1/2 v. And this is 1/2 u minus 1/2 v. I don't want to get anyone tempted in thinking that they need to use a quotient rule, right? So just distribute this division by 2 to each piece. And now maybe it's a little bit more clear, right? If I take the partial derivative of my x with respect to u, I'm going to get 3/2. If I take my partial derivative of x with respect to v, I'm going to get negative 1/2. Next up, y information. Y with respect to u is going to be 1/2. And y with respect to v is going to be negative 1/2. Calculating out my determinant, I'm going to have what? Negative 3/4. And I do my first diagonal. And then minus a negative 1/4. So that's going to be negative 2/4, or that's the same thing as negative 1/2. So this is a place where if I was to just put negative 1/2 here, I'm going to get the wrong answer. This is a place where the absolute value really does come into play. So remember, it's not just the Jacobian that goes here, it's the absolute value of the Jacobian. So again, on our formula here, not just the Jacobian, but the absolute value of the Jacobian. Because we're changing areas. All right, the last thing, and usually what I find to be the most difficult, is swapping out our bounds, right? So I want to know, what do our bounds look like in terms of u's and v's, rather than in terms of x's and y's? Well, first I kind of need to figure out, right, I know that they join these points together, but I don't even know what really these equations are, right? I know that they're all lines. So for instance, I know that this one right here, maybe this bottom piece, right? It's a part of a line. So I know it's going to be y equals mx plus b, for instance. But I don't even know what the equation is, right? So I need to spend a little bit of time figuring out this equation. So one thing that we could do is we could figure out the slope, right? So this point here is 1, 2. And this point here was what, 4, 3? So our slope is supposed to be our rise. So it looks like from 2 to 3, we rose by 1, divided by our run, right? So we went from x equals 1 to x equals 4. So it's going to be rise divided by run is going to be 1/3. Again, formally, you can do this equation, y2 minus y1 divided by x2 minus x1 if you'd like. In which case, right, you have 3 minus 2 divided by 4 minus 1. So if you want the very algebraic equation way of calculating this out, you can, or you can just look at it and kind of, you know, the rise from 2 to 3 is 1, you know, the run from 1 to 4 is 3. All right, so I have my slope. The last thing I need is my intercept. So I know that this is equal to y equals 1/3 of x plus b. So I need to know what that b is. So I'm going to plug in one of my 2 points. Either one will work perfectly fine, and figure out what b has to be. So in this case, right, I'm going to plug in maybe 1, 2. So I get an output of 2, a y value of 2. If I plug in x equals 1. And so this gives me a b of 5/3, right? 2 minus 1/3 is going to be 5/3. So y equals 1/3 x plus 5/3. All right. Well, now that we have this, we know what it looks like in terms of x's and y's. Now we can go ahead and use our transformation equation on this. So our transformation equation says that x should be equal to this 3u minus v over 2, and that y should be equal to this u minus v all over 2. Or we, of course, have this written in the other way. So, right, let's see. X is equal to 3/2 u minus 1/2 v. And y is equal to 1/2 u minus 1/2 v. And now we need to solve this in terms of u and v, right? So, well, I do have what my y is equal to here. And so we could reduce down by kind of plugging this in down here, for instance, is maybe one thing that I'm thinking about. So why don't we go ahead and try that? So that's going to be 1/3 x plus 5/3. I do notice as well that it seems like maybe we could cancel some things out here. We have a negative 1/2 v in both of these. So I'm interested in maybe taking my first equation and subtracting away my second one. So I'm going to take this x being 3/2 u minus 1/2 v. And I'm going to subtract away my second equation. Again, at this point, we're just solving a system of equations. I'm not doing any calculus or whatnot. This is me just trying to do the algebra behind solving for u and v in terms of x's and y's. Oh, sorry, I got distributive happy here, and my second equation should have minus 1/2 v. So now I distribute here, and this is going to give me 0 v's. That's kind of why I'm doing this here. 3/2 u minus 1/2 u is just going to be equal to u, or 1 u. And then on the right-hand side, let's see, I'm going to have 2/3 x minus 5/3. Okay. Well, the last thing that I can do, right, in order to get this all in terms of u's and v's, which again, I was trying to get all my x's and y's into u's and v's, is to get rid of my x, right? So again, x back here, I guess I could have done this earlier even too. Again, x was equal to all of this stuff, the 3/2 u minus 1/2 v. I might as well change that in now. Again, I probably could have done that even earlier. 3/2 u minus 1/2 v. And if I go ahead and I distribute, let's see, this is going to give me u minus 1/3 v. The u's on both sides can cancel. That's quite nice. So subtract u on both sides. I can bring my 1/3 v over to the other side. So I get negative 5/3 is equal to 1/3 v. And then I can multiply by 3 on both sides. So this is going to give me v is equal to negative 5. So all that to say that when I use our transformation and I transform this bottom side right here into my UV plane, it's very, very nice. It's just v equals negative 5. So this line here in the UV plane has become v equals negative 5. Now, I don't know if that's the smaller or the larger one, right? So maybe there's a negative 5 down here, or maybe there's a negative 5 up here. I don't really know. It turns out the other values, I see that we're over time, I apologize. So when you transform all the other ones, you get v equals negative 9, u equals 1, and u equals negative 1. So our bounds here would be from negative 9 to negative 5, negative 1 to 1. So that's the setup. It's a pretty easy integral, similar to like our last one. So once you have the setup, that's really the difficult thing. So please go ahead and try to evaluate out this integral on your own, and I'll post the solutions by 3 o'clock today. All right, thank you very much, everyone. I'll see you on Wednesday. We'll talk about polar coordinates.